Lesson 2-7, Graphing Inequalities. Here's what the examples look like. So we want to graph 2x plus 3y is greater than 6. Okay, so the first thing that we want to do is we want to solve this inequality for y, because if I solve it for y, then I can use the y-intercept and the slope to graph the line. So let me just recopy it. 2x plus 3y is greater than 6. I want to get y by itself so that it's easier for me to graph. So I'm going to subtract 2x on each side. These will cancel out, and I'm going to rewrite it. 3y, the sign stays greater than, and over here I'm going to put the x's first so that it's in slope-intercept form. So it's a negative 2x and a positive 6. Okay, then I'm going to divide both sides by 3, and I've got it solved for y. Now when I divide this side by 3, instead of dividing the whole thing by 3, you can split it up into two fractions. So negative 2x over 3 is negative 2/3 x. That's your slope. Plus 6 over 3 reduces to 2. So now here's our inequality in slope-intercept form. Y is greater than negative 2/3 x plus 2. Okay, so when it's written in this form, you could type it into your graphing calculator. That's an easy way to graph it. Or you can identify that 2 is the y-intercept, and negative 2/3 is your slope. That's the rise over run. So let me show you how to graph it without a calculator. The y-intercept of 2 is right here. That means this is where the line's going to cross the y-axis. Negative 2/3 is my slope, so from this point I'm going to count down 2 over 3. There's my next point, down 2 over 3. I can also go backwards and go up to the left, up and to the left, and there's some points on my line. Now, the difference is we're not graphing an equation, we're graphing an inequality. So if I see in the equation that strictly greater than or strictly less than, we actually are going to make our line dashed. So I'll do my best here to connect the dots. We're not using a solid line because what we're saying here is graphing this inequality on a coordinate plane, the points that are on the line are not included in the solution set. That's what we're saying by making this line dashed. The symbol says strictly greater than, so these points are not included in the solution. Now, the other part of graphing an inequality is that you have to shade either above the line or below the line according to the symbol. Because this symbol says, right here, because it says greater than, I'm going to shade all of the points above this line. Okay, now here's what we're saying. Anything in this shaded region is a solution to this inequality, not including the points on the line. So for example, if I pick the point 0, 3, that's in my solution set. That's in the shaded region. Another point in the solution set would be 4, 4. Anything in the shaded region is a solution. What that means is if you plug in the point, for example, 0, 3, for x and for y, 0, 3, we're going to get something that's greater than 6. Okay, so any point in here would satisfy the inequality if you plug in the x and the y values. All right, here you've got the steps for solving these inequalities, exactly what I just showed you. You're going to start by solving the inequality for y, identify the slope in the y-intercept so that you can graph the line. Before you connect the dots, you need to think to yourself, is it a solid line or a dashed line? A solid line means you're including those points on the line. So you would only use a solid line if the symbol has an equal to underneath it. You're going to use a dashed line for strictly less than or strictly greater than. And then finally, your last step is to shade above the line or below the line. And you only need to do this for inequalities. Let's do another example. Okay, so following those steps again, I'm going to start with the original inequality, 3x plus 1/2 y is less than or equal to 2, and I'm going to start by solving the equation for y. So I'm going to subtract 3x from each side. 3 minus 3 is nothing. Over here, I'm going to be careful about rewriting it. I've got 1/2 y is less than or equal to. Now instead of writing 2 minus 3x, I'm going to start with negative 3x plus 2, because I want the x to be first so that I can find my slope. Okay, and remember, these are not like terms, and so you're going to write them separately. Negative 3x plus 2. Now, instead of dividing both sides by 1/2, it's actually smarter if we multiply by 2. Multiplying by 2, 2 times 1/2, those are reciprocals, so I'm left with y is less than or equal to. On this side, when I multiply by 2, I need to multiply the entire side by 2. And so I'm going to use the distributive property. We get negative 6x plus 4. 2 times 2 is 4. And now we can graph this. My y-intercept is 4. So I'm going to start on the y-axis at 4. That's where the line's going to cross the y-axis. And my slope, the number times x here, is negative 6. I'm going to think of this as negative 6 over 1 because I want to graph the rise over run. So that means from 4, I need to count down 6 to the right 1. Negative 6 over positive 1. Okay, so there's 3 points on the line. I need to now check my symbol to make sure if my line is solid or dashed. So I want to make sure that I'm drawing the correct line. There is an equal to underneath this symbol here in the original equation, so I can connect these with a solid line. Nice and straight, as straight as you possibly can. This line goes on forever and ever. And then I need to decide where to shade. Now the symbol says less than or equal to. You have to be able to read these symbols. Less than or equal to means shade below the line, and this line is slanted, not very much, but it is slanted, and so below the line is actually to the left here. But you can't always think left or right. You really have to think above or below when you're going to graph. Now, if you wanted to check that you've got the correct shaded region, what you could do is pick a point in the shaded region and test it. So I notice right away that 0, 0 is in the solution region. So I'm going to test 0, 0 because it seems like an easy point to test. And that'll tell me if I shaded the right side. So in the original equation, I'm going to plug in 0 for x, 0 for y. So I'm substituting 0, 0 in for x and y, and it should give me an answer less than or equal to 2. Well, obviously 3 times 0 is 0, 1/2 times 0 is 0, and 0 plus 0 is 0. So the point 0, 0 works in the equation, and that tells me that this is in fact a solution, and so is everything else on this side of the line. Okay? Anything to the right of this line or above the line would not work in the equation, and that's how you could check your answer. All right, let's try a couple more graphs. This time we're involving absolute values. So in order to graph absolute value, there's really no easy way. You could find the vertex or the center of the graph, draw the right side, and then match the left. You could use a graphing calculator. That's the way I'm going to do it in class. You could also make a table. For purposes here, I'm going to make a table, and I'll show you what the table looks like. So x and y values here. I'm going to plug in -2, -1, 0, 1, and 2. If I plug in these x values for x here, I can figure out what the corresponding y value is. So when I plug in -2, the absolute value of -2 is 2, 2 plus 1 is 3. When I plug in -1, the absolute value of -1 is 1, and 1 plus 1 is 2. When I plug in 0, I get 1. When I plug in 1, I get 2. And when I plug in 2, I get 3. So very quickly, there's a table. Plugging in x values and then writing down your answer for the y value. Okay, now let's plot these points. We should know that absolute value graphs are V's, and that's what we're expecting to see here. -1, 2, 0, 1, 1, 2, 2, 3. Okay, and here's the center of the V. It's going to go up and to the right on this side. I know I'm not very accurate, and up and to the right on this side. Now I should have, before I connected my points, I should have checked out the symbol and asked myself, is it solid or dash? But I'm okay here because there's an equal to underneath the sign. I was supposed to make it solid, so that's good. Remember, if that equal to is not there, you're going to make a dash line. The last thing I need to do is shade. This sign is less than or equal to, and so it makes sense that I want to shade everything below this graph. This is what my shaded region looks like. Now this shaded region goes on forever and ever. Every point below this absolute value graph is in the solution region for this inequality. Again, if you wanted to test one, test a point, an easy point that's in the solution region. Well, 0, 0 happens to be in the solution region. Let's see if it works. 0 is less than or equal to the absolute value of 0 plus 1. Well, 0 is less than or equal to 0 plus 1 is 1. And yes, that's true. And so we've checked to make sure that we've got the correct solution region on our graph. Okay, last one. Let's try a word problem here. A mail order company is hiring temporary employees to help in its packing and shipping departments during their peak season. Write a graph in inequality to describe the number of employees that can be assigned to each department if the company has 20 temporary employees available. Well, we can use X here to represent the number of employees for packing. So I'm just going to quickly write, so I don't forget, I'm going to write it down. X is packing employees, and let's say that Y represents the shipping employees. Okay, packing and shipping, but we're talking about people here, the employees. The number of employees that can be assigned to each department is only 20. So that means that X, the number of packing employees, plus Y, the number of shipping employees, has to be less than or equal to 20 people, 20 temporary employees that are available. If we want to graph this here, you could make a an X and a Y table, or you certainly could solve this equation for Y, and that's what I'm going to do because it's really simple. I'm going to subtract X on each side. Y will be less than or equal to, that's negative X or negative 1X plus 20. Okay, so let's go ahead and graph this. This is in slope-intercept form, so I know that 20 is my y-intercept, and it looks like the number times x here is negative 1, so negative 1 over 1 is my slope. I'll show you what the graph looks like. Going onto the y-axis, 20 is our y-intercept, so I know there's a point there. And the slope is down 1 over 1. Down 1 over 1, down 1 over 1. It's going to look like this. Now, I should ask myself, can I connect these points with a solid or a dashed line? I can make a solid line here. However, this line does not go on forever and ever and ever. It's going to stay in the first quadrant because I can't have negative amounts of people. And so we're only working with positive x and y values here. So the line stops when you hit the x-axis and stops at the y-axis. Now, any point underneath this line is a solution. Let me explain why. So here's our shaded region. Any point, again, staying in the positive numbers, any point in here is a solution. Remember what we said. X is the number of packing employees, and Y is the number of shipping employees. I'll label this sloppily. There you go. Okay, so what I'm saying here is we can pick 6 people to help with packing and 12 people to help with shipping because that's still under 20 employees. I could pick 10 people to help with packing and 10 people to help with shipping. That's the very edge of our boundary, but it is in our solution region here. 10 and 10 makes 20. I could pick 14 people for packing. That only leaves me with 6 people for shipping, but I'm still using 20 employees. So I can't go over using 20 employees, but any combo in this triangle would work for this company. That's all we're saying. Okay? And obviously, if you wanted to use all 20 employees for shipping, that would put you at this point up here. There's 0 employees left over for packing. All right. Finally, I want you to try this one on your own and bring it to class with you tomorrow. Simply graphing a line and then think about if it's solid or dashed and where you should shade.